Yeah, okay. So are you able to see my screen, which I am sharing?
Yes, sir.
Yeah. Okay. Today I am going to solve the previous year assignment number 4. So this class is regarding the week 4. Okay. So I am Subhajit Basak, the PMRF Scholar from IIT Bombay, and you of course know the this course is taken by Professor Mahesh Patil from IIT Bombay itself. Okay. So today most of the questions are about the half wave rectifier and also about the transistor, that is a BJT, bipolar junction transistor. So I am start solving one by one. So in the first question, it is asked about assume that NPN BJT have VV 0.7 volt in active and saturation mode, and the VC saturation voltage is zero point 0.2 volt in the saturation region. And similarly for a PNP BJT, assume that VEV is zero point 0.7 volt in active and saturation modes, and VEC saturation is zero point 0.2 volt in the saturation region. And we should consider the VT as 26 millivolt at 3000 Kelvin, that means at room temperature, and beta to be large unless specified. Okay. So I want to tell some of the things like suppose there is some BJT. Suppose this is NPN BJT. So this terminal is emitter E, this terminal is base B, and this terminal is collector C. Okay. So so this is basically a three terminal device, and we can see there is a two junction. Here it is PN junction, one PN junction, and here it has also another PN junction. So this BJT, it refers to bipolar bipolar bijunction transistor. Okay. So bipolar refers to that holes and electrons both are carriers in case of a BJT, bipolar junction transistor. So the current conduction happens due to holes as well as due to electrons. So for NPN transistor, the electron are the majority carrier and the hole are the minority carrier. So it happens due to both of the majority carrier. The current flow happens due to both of the majority carrier and the minority carrier. So it is known as a bipolar transistor. And again, bijunction, that means there is a the both the junctions are there at the emitter base junction. One is emitter base junction. This junction is known as emitter base junction, and this junction is known as a base collector junction. So both the junctions are present. So that's why the name is bijunction comes from. Okay, came from. So this is bipolar bijunction transistor. Okay. So uh, actually, you know that if there is some PN junction diode, so we can bias it in two situation. Like we can give this P terminal. This is known as P terminal. This is known as N terminal. So you can connect the potential, positive potential to P terminal and negative to the N terminal, or either this or the negative terminal to the P junction and the positive bias or positive potential to the N terminal. So basically here also there is NPN junction. So here also you can make it positive negative, or here also you can make it positive negative. So based on that there are some operation mode of the transistor. So this is so mode of operation, that is the base emitter junction, there is collector base junction, and this is known as operation mode. Okay, operation mode. Okay. So suppose we have connected the base emitter junction as forward bias mode and collector base junction as reverse bias mode. So then it is known as the transistor will act in active region. Okay. So in case of NPN, if we connect this base emitter to the forward bias, that means negative terminal is connected to N and positive terminal is connected to P. Okay. And here the base collector junction should be in the reverse bias. That means the P is connected to the negative terminal and N should be connected to the positive terminal of the potential, right? So when we apply this bias condition, that is the base emitter forward bias, this is forward bias, and the base collector reverse bias, then the transistor, that is the NPN BJT, this BJT works as worked at works at active region, right? And if we change the case, like it is reverse bias, this is forward bias, then it can work in reverse active region. Okay. Similarly, if we apply the base emitter junction is forward bias, collector base junction is forward bias, then it work at saturation region. And if we apply reverse bias to both of the junction, then it work at cutoff region. Okay. So basically, generally we depending on the application we apply the bias. Suppose we want to amplify some input signal, then the transistor should be act as in active region. Okay. And otherwise if we want some switching application, then we should operate the transistor in the either in the saturation region or in the cutoff region. In saturation region, what happens, it can act as an on switch, and in the cutoff region it can act as an off switch. Okay, so these are some basic things. So basically this VBE is 0.7 volt. So if we draw any, this is NPN, this transistor. So this is the emitter, this is the base, and this is the collector. So here is some PN junction and there is a drop of 0.7 volt. Okay, so this VB refers to this voltage drop across this PN junction. You already have studied, like this is the 0.7 volt is a cut-in voltage in the PN junction. So that depends on the material which you are using. Suppose for silicon it may be 0.7 volts, for other materials it will be changed. For gallium arsenide it will be much more than that. Okay. And this VC saturation, that means the voltage drop across the collector and the emitter. So this VC should be greater than 0.2 volt, otherwise it will go to the saturation mode. So if it is greater than 0.2 volt, then only it can act as an active region. So these informations are given. And also I want to tell you about the beta. Okay, so basically in a transistor there are three current. So one is the IB, that is the current flowing through the base terminal. This is IC, that is the current flowing through the collector terminal. This is IE, the current flowing through the emitter terminal. So for any transistor like NPN, either it be a NPN or PNP, the current flowing through the emitter terminal is the summation of IB plus IC, that the current flowing through the base terminal plus the current flowing through the collector terminal. So what happens in case of NPN? Suppose in NPN, so in case of NPN, so this is emitter, this is base, and this is collector. So this is the NPN, N terminal, P terminal, N terminal. So what happens? So this IC and this IB both combine to form IE. So IE basically IB plus IC, right? And in case of PNP transistor, what happens? So suppose this is P, this is N, this is P, and this terminal is the emitter terminal, this terminal is the base terminal, this terminal is the collector terminal. So the current flowing to the emitter terminal, that divides into two parts, which is IB plus IC. Okay, so for either of these two type of transistor, I is always the summation of IB plus IC. And basically what is the suppose there is some, so what is the fundamental things, that is how we can operate a transistor, that I am showing. This is some bias value VCC, this is some bias voltage. Either we can take the VBB from here, then it is called as a single voltage source. Using the single voltage source, we can apply the bias both to the collector terminal and the base terminal, or otherwise if we want to make it a double source, then we apply two battery terminals or two potential differently in the collector and the base region. Okay, suppose here we want 10 volt and here we want 5 volt, then we do not and we have to make it using a single source, then we can use a voltage divider simply over here. So we are putting 1 kilo ohm here, 1 kilo ohm here, so this 10 volt appears to 5 volt over here, and thus we can supply the 5 volt to the base terminal. So we can use a single source also, or in the other way, like we can use a 10 volt battery here and 5 volt battery here separately, and we can put the input or feed the input to the transistor. Okay, so this terminal is known as base, this is collector, and this is the emitter. Okay, so now what happens is, so we can we are giving the input VBB. So there is something VB, that is the voltage, that is the 0.7 volt drop across the base and emitter terminal. So if we increase VBB, or if we can decrease VBB, then according to that we have some fixed value resistor RB, RE, RC, let's say. So what happens if we increase VBB? Then what happens? This IB, that is the current flowing through it, it can increase, and this terminal is known as the input terminal, that is the input side. So what happens, like this, some IB current is flowing through this, and this IB multiplied with beta forms the IC, that is the collector current, and this collector current flow through this IC, and this side is known as the output side. So sorry, so we can use some input KVL and output KVL in both the terminals, and can determine what is the current flowing through each of the terminal, or we can find out what is the value of the resistor that we can put. So I will discuss this more if we move forward. So what I was discussing about the beta. So basically the current through the collector is nothing but the beta time multiplied by current flowing through the base, IC equal to beta IB, and similarly IC equal to alpha IE. So we can easily found out that what is the relation between alpha and beta. So alpha is nothing but beta divided by 1 plus beta. So this is number one equation, this is number two equation, and as I have already discussed, the IE is nothing but IB plus IC. This is the number three equation. So if you put this value, IC value here, and also this value here, so we can easily find out the relation between alpha and beta, and it turns out to be alpha is equal to beta divided by 1 plus beta, and beta is nothing but alpha 1 minus alpha. So that is the thing. So here in the question it is told, like, if beta is very large, that means if beta is infinite, if beta is infinite, beta is very large, then what happens? Alpha is nothing but, as I have already discussed, beta divided by 1 plus beta. So I am dividing beta to the both the sides, so 1 divided by 1 plus beta plus 1. Now if we put beta is infinite, that means very large, then this alpha comes out to be 1 divided by 1 by infinite becomes 0 plus 1, that means 1. So alpha becomes 1. That means this IC should always be equal to I, right? Alpha equal to 1. So if we put in this equation, equation number 2, we are getting IC is equal to IE. So whenever there is no beta mentioned in the question, then we can always follow, or we can always use this equation. IC is nothing but equal to IE. But we know that IE is equal to IB plus IC according to question number equation number 3. So that means this IB is equal to 0. That means there are no current flowing through the base terminal. Okay. So I just derived this thing. So moving forward, I will if there is mention like beta should always be large unless specified, then you should always consider that means that refers to IB is equal to 0, and the emitter current should be equal to the collector current always. Okay. So do you have any question regarding this till now?
No, sir.
Okay. So okay, so I am going through the first question. So this question is about the half wave rectifier. Okay, so consider a half wave rectifier Vm equal to 25 volt and frequency is 50 hertz and the capacitance is 500 microfarad. If the ripple voltage is to be limited to 2 volt, what is the lower limit of the load resistance? Okay, and diode is consider the diode to be ideal. That means if it is turns on, then it doesn't apply any potential and it is simply 0 volt. That means the diode becomes directly short circuit. Okay, so at first I am drawing the rectifier. So suppose this is the thing, and there we are applying capacitor and also we have some resistor. Okay, and this is some diode and this is the source, suppose V in. So here in the question it is told like consider half wave rectifier with Vm equal to 25 volts. Suppose this V in is nothing but yeah. So V in is Vm sine omega t. Now in the question it is told Vm is 25 volt and this omega is 2 pi f radian per second, right? Radian per second. So twice pi f, the frequency value in the question it is told like 50 hertz. So that means 100 pi radian per second. Okay, radian per second. So this is the omega value. Now I am drawing the input voltage. So suppose this is V in versus the time omega t or t. Okay, so the peak value is Vm. So this is the peak value. So Vm, this is the peak value, and here it is the minus Vm. So this V input is Vm sine omega t. So what happens is like at first if the Vm becomes positive, at first the V in input is 0. So here the 0 volt is applied and here also the potential is 0. That means the diode is not in the on condition, it is in the off condition. So whenever this V in is positive, that turns the diode on and it will replace by the short circuit. So the current can easily flow and charge the capacitor. Okay, so the capacitor will instantly get charged. Why instantly get charged? Because Now so there is a short circuit path, so there is simply the tau is nothing but the on resistance of the diode into C capacitance, and this on resistance of diode is very small, very small. So that means the time constant becomes very small. That means at a very small time it got fully charged. So the capacitor value follow the input signal and it got charged. So till this point Vm, the capacitor got charged. So when the input voltage reaches Vm, then the voltage across the capacitor becomes Vm over here, and here then again the voltage drops. That means the voltage is now this side the voltage is Vm, but in here it is less than Vm. So the diode becomes the reverse bias. That means this diode offers a open circuit in this point, and so no current flows in this direction. So now whatever the charges that is accumulated in the capacitor, that gets discharged through this point, through this resistor, right? So there is some certain time constant, that is the value of this resistor R and C. So according to that it will discharge, and again when it gets in this position, so again when the input voltage becomes greater than this, then the capacitor again gets charged and again it will discharge, and again gets charged, again it will discharge. So like that the output waveform will be like this. Okay, so in the question it is asked that this ripple voltage, uh, if the ripple voltage is limited to 2 volt, okay, so the difference between this Vm and the ripple voltage, that means this should be 2 volt. Okay, so if it is 25 volt, so it should be 23 volt. Then what should be the value of the resistor? So you understood, right? So if the resistance value is too low, right? So there should be some lowest value of the resistor, right? There should be some lowest value, because if R is even low than the lowest value, then the time required will be very large. That is, the time constant should be very large, and then this the capacitor will discharge to further more down, right? So capacitor will discharge and it will cross the 23 volt, right? So there should be some limitation of the resistor value. So uh, if the resistance value is more than that, then it will be better, right? It will not go beyond 23 volt, but it is even if it is even less than that, then it will go beyond the 23 volt. So there should be some limiting value of the resistor, and we have to find that one. Okay, so how should we proceed? Like, just one second. Okay, so what happens is like, so this capacitor, so so there will be some discharging of the capacitor. So the capacitor initially charges to 25 volt, and as I have already discussed how to find out at any instant of time the capacitor voltage, that is nothing but the final value plus initial value minus final value into e to the power minus t by tau, right? Where tau is nothing but the time constant, as I have already discussed in the earlier lectures. Okay, so now what happens is, like, if this resistance is connected to a long time, that means for the long time the diode is off, then the capacitor charge will discharge fully, so the final value will become 0, and the initially the capacitor is fully charged. That means before at this point, right? So we are considering at this point it is fully charged, and if it discharge for a long time, then it will become 0. right? So this is the final value 0 and this is the initial value, which is nothing but Vm, that is 25 volt. Okay, so this is 25 volt. So from this equation we get Vct is nothing but 0 plus 25 minus 0 into e to the power minus t by tau. That means this Vct is 25 e to the power minus t by tau. Okay, so now in the question it is told the ripple should not be less than 2 volt. So that means 23 is equal to 25 e to the power minus t by tau. Now how should we get this t? So this t is nothing but from here to here. Okay, this is t, right? And this capacitor, when it gets charged, that is some considered t1. So this and this is the total time period of the signal. The input signal time period is capital T. Okay, so this capital T is nothing but t plus t1, and this t1 is very small, so we can ignore this t1 and we can say t is almost equal to capital T, that is the input signal time period, right? The time period of the input signal. So here this t we will replace it by 1 by 50. Why 1 by 50? Because the input frequency is 50 megahertz, so time period will be 1 by 50, and that we will consider as a t time period, and this tau is nothing but r into c. So 23 is 25 e to the power minus 1 divided by 50 into r into c. C value is given in the question, it is 500 microfarad. So from here you can see ln 23 by 25 is nothing but minus 1 by 50 into r into 500 into 10 to the power minus 6. So r is nothing but 1 divided by 50 into 500 into 10 to the power minus 6 into ln 25 by 23, right? Because this minus, if we multiply minus, then it becomes 25 by 23, and then we put r here and this equation here, and we get this one. So if we solve this one, this thing, so I'm trying to solve this. This 10 to the power 6 becomes 1000 into 1000, that's means 10 to the power 6 in the upper side. This is 50, this is 500, and this is ln 25 by 23. So these two cancels out, 2, this is 25, this is 40. So 40 divided by ln 25 by 23. So now I am using calculator. So 25 by 23 ln, so it comes out as a 480 ohm. So this resistance value should be 480 ohm. So according to the question, this value, so 480 ohm is close to 500. So taking some approximation or something, so this 500 ohm should be the limited value of this resistor. Okay, so what is the physical interpretance of this? That if we increase the resistance value from, so answer is 500 ohm, right? So if this resistance is 1000 ohm, that means the tau should be much more large, and then suppose this voltage drop would be the ripple voltage would be 1 volt or something like that. Okay, and if this resistance value is small, then it will discharge more and it can come up to 22 volts, suppose. So like that, so there should be some limitation value of the r for which it should not go beyond 23 volt. That means the ripple voltage difference between the ripple voltage should not be go beyond 2 volt. So this 500 ohm is the limitation of the r, and that we found out. Okay, so do you have any question regarding this? Do you have any question? Yeah, just 1 second. Yeah, please. Hello. Hello, Shankar, you can unmute and tell.
Sir, can you hear me?
Yeah, sure. Yeah.
Okay, what happens if it is a inductive load
What
instead of
happens?
resistive load?
Okay, then in case of the inductive load, right?
Yes.
Yeah, so then you have to mm, mm, okay, okay, I have to see about it then what it should be. Uh, okay, it will be better if I see and then answer in the next class. Okay, is it
Okay,
okay?
sir.
Yeah, sure. Okay. So for the next question, okay. So for the question given, for the condition given in question 1, what is the average diode current? So it is Vm sin omega t. So this is some current, there is some current, and there is some current flowing to the ID. So this diode current is nothing but IC plus IR, and this ID is C dVc dt plus this resistance current, which is nothing but Vm divided by R, because the capacitor once fully charged, then this voltage will drop across it, and this ID becomes C d dt of this. This is nothing but Vm sin omega t, that is the voltage. This is this voltage Vm sin omega t, C dv dt, this one, plus Vm by R. Okay. So for what condition given in question 1, this is the average current. Okay, so we have to find out this ID average. ID average is nothing but the current, the average current flowing through the capacitor plus this average current flowing through the resistor. So you can see when the diode is on, so then this is Vm sin omega t, and this diode becomes on, then there is some current flowing through the capacitance, and there should be some resistance. So this ID is nothing but IC plus IR. Okay, and whenever the diode is off, that means, so there is a capacitor and there is a resistor. Okay, so once the capacitor is charging, and in a second time the capacitor is discharging, so basically this IC average value turns out to be 0, and this ID average value become equal to IR average value. So IR average value is nothing but it is Vm sin omega t, so that this Vm appears over here, so it is nothing but Vm divided by R, and Vm is 25 volt, and this R resistance that we found out is 500 ohm, right? So this is 500 ohm. So this is coming out to be 25 into 1000 divided by 500 milliampere. So comes out to 50 milliampere. Yeah. So for the condition given question, what is the average diode current? So that will appear to be the 50 milliampere. So what happens is, when what is the average current that is flowing through the diode, that will be divided into two parts, that is the current flowing through the capacitor part and the current that is flowing to the resistor. And now in the first case, if the diode is on, then the capacitor is charged. So and if when the diode is off, then there is no connection between this and the capacitor will discharge. So if we plot these two things, the capacitor charging and capacitor discharging, then if we find out the average, then that average will that the area under the curve will cancel out, and it comes like the IC average value is equal to 0. So whatever the value of this IR, that will reflect to the average value of the ID. And how to find out this IR average? This is nothing but Vm, that is the magnitude, divided by R, and Vm is 25, and if we put this value, then we get it is to be a 50 milliampere. Okay.
Sir, how it is going to cancel out?
Okay, actually you have to plot then how it will be this capacitance value. So this is, so the capacitor get charge and then it gets discharge, then charge, and then again gets discharge, this thing. So here actually it is mentioned in the lecture also, if we follow the lecture.
Approximately, if you can.
It's mentioned actually. I think I am running very late because it's already 45 minutes, so I have to cover the whole thing within 2 hours. So okay, it's mentioned in the lecture. If you don't find it, then I can explain in the next class actually, because only two question is covered till now. Is it okay? Okay. Yeah. So for the condition given in question 1, what is the peak diode current? So Vm sin omega t, this is the resistor, this is the capacitor, this is the current, the, that is the ID. Okay. So now so what is the peak diode current? So as I have already discussed, the diode current is nothing but the combination of IC plus IR. Okay. So this diode current is IC, the current flowing through the capacitor, which is nothing but C dV dt, plus the IR. IR is nothing but Vm divided by R. Okay. So it will be C d dt of Vm sin omega t plus Vm divided by R. So if we took the derivative, C into Vm into omega, sin omega t's derivative is cos omega t plus Vm divided by R. Okay. So this will be the diode current ID. So now if we plot the input voltage, so So this capacitor gets charged over there, and then it gets discharged, and then again it gets charged, right? So it discharged till 23 from 25 volt. So we need to find out the value of omega t, right? So so the capacitor, when it is getting discharged, so this 25, so this V in value should be equal to 23, and 25 sin omega t is nothing but 23, so omega t will be sin inverse 23 by 25. And if we replace in this diode equation, it will be id c vm omega cos of, this is sin inverse 23 divided by 25, and this vm you can take it 25 divided by r means 500. Okay, yeah. So we are just considering this thing to be the omega t, uh, yeah, and this comes out to be 500 microfarad into this vm value, that is 25 into 2 pi by 50 into cos, so sin inverse 23 by 25, once again 23 by 25 sin inverse, so this is 66.92 degree plus 25 by 500, so this is 500 into 10 to the power minus 6 into 25 into 2 pi into 50 into cos, yeah. So it is coming out as 1.53 ampere plus 25 divided by 500, so it is 0.05 ampere, so it is 1.58 ampere. So this 1.5 ampere is nothing but the peak diode current. Okay, so the correct answer will be 1.6. Yeah. Okay. Okay, so for the next question, for the given question in question 1, condition in question 1, what is the maximum reverse voltage across the diode? So this is the V in, and this is the time period t. So this is the Vm sin omega t, and this is the minus Vm sin omega t, that is 25, and this is minus 25. So for this region, capacitor gets charged and the diode is on, and through this region capacitor gets discharged and the diode becomes off. Okay, okay, so the okay, so the diode becomes off. So that means from the circuit we can see this Vm is applied in this terminal, and here it is the output. Okay, so this, so it is nothing but so V across diode is nothing but V in minus VO. So the input voltage maximum value is 25 because it is Vm sine of omega t. So Vm value is 25 and this is the output voltage. So this output voltage is nothing but the voltage across the capacitor. So the capacitor can charge till 25 volt, and so this 25 volt, so if it suppose if it retains the 25 volt also, then the diode was also off. So maximum the voltage minus 25, that means this 50 volt can appear as a maximum value for the diode to be in the reverse bias. You understood, right? There is a diode, so this is V in, that is nothing but Vm sine omega t, and in this region it's the V out, that is the output. So the capacitor is discharged like it is now, it is 23 volt, but maximum it can retain its own charge if the value of R is suppose it is very high, then the time constant is very high, so it will discharge a little bit, so it can be close to 25 volts. So 25 minus of minus 25, so that means this 50 volt can be appeared as a maximum reverse voltage across the diode. Okay, yeah, okay. So moving forward to the next question. So consider a NPN BJT operating in the active mode at room temperature. So suppose there is NPN. This BJT is operating in the active mode in room temperature. So this is the emitter, base and collector. Okay, so let IC is 2.5 milliampere for some value of VB. Okay, so some value of VB, by increasing VB by delta VB. So what is the we want to increase IC. So you have already seen in the lecture, it is described that IC can be written as this saturation current into e to the power VBE divided by VT, right? So this is 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 called as a saturation current. So whatever the input voltage we are applying, and this IC can be written like this. So now what it is told, that the IC value is 2.5 milliampere for some value of VB, say VB1. So IC1 is IS e to the power V VB1 by VT, and IC2 is, if we increase VB by delta VB, right? So IS e to the power V VB2 divided by VT. So if we put this value, so it becomes 2.5 is nothing but IS e to the power V VB1 divided by VT, and this IC2 is nothing but so it is 4 milliampere, right, equal to IS e to the power V VB2 by VT. So this is equation 1 and this is equation 2. So if we divide equation 2 by equation 1, 2 by 1, then we get 4 divided by 2.5 is nothing but IS cancels out, so it will be e to the power V B2 minus V B1 by VT, right? So V VB2 minus VB1, that means delta VB is equal to VT ln 4 divided by 2.5. So VT is 26 millivolt at room temperature. 4 divided by 2.5, it is 1.6, so it is ln 1.6. So ln 1.6 into 26, that comes out to be 12.22, that much millivolt. Okay, so that means if we increase this, the value of delta VB to 12.2 millivolt, then the IC value will increase from 2.5 milliampere to 4 milliampere. Okay, Okay, so the next question, consider an NPN BJT operating in the active mode at room temperature. Okay, if VB is reduced by 0.02, what is the percentage reduction in the collector current? So the same equation we can write, IC is nothing but IS e to the power V BE divided by VT. So IC1 is Is e to the power V V1 by Vt, and IC2 is Is e to the power V
Sir,
V2 by
can you explain
Vt.
the
Yeah,
seventh part again?
sorry,
Sir, can you explain seventh part?
seven part. This one,
The seventh question.
this one.
Uh,
Which question you are talking
I
about?
think, sir, that it's like some question of food.
Sorry, I'm not getting. Can you repeat?
They're like one.
Your voice is breaking. Can you?
Hello.
Yeah, hello. Yeah, tell me.
So like you're discussing from assignment only, right?
Yeah.
Like I didn't find your questions in assignment.
Yeah. This is the previous year assignment.
Okay.
Yeah.
Okay, sir.
Okay.
Sir, where can we see
Sorry.
previous year as where can we see previous year of assignments?
Okay. So basically, okay, I will share this to you in the team.
Can you share the link now?
In the link you can't see because it is some confidential or something. So we have a particular Gmail address, and from there we can see the things and we can solve this question. So I think we'll not be able to see, but I can share the questions also in this chat box. Should I share?
Yes, sir.
Okay, so what I will do, I will share it here after this meeting, and I will send the link. I will upload it in the Google Drive something, and I will share the link in this chat box. Okay.
Okay, sir.
Okay. So consider an NPN BJT operating active mode room temperature. If VB is reduced by zero point 0.2 volt, zero point 0, what is the percentage reduction of the collector current? Okay. So this is the thing. So similarly, if we do like IC2 by IC1, that is dividing the equation 2 by equation 1, then we are getting e to the power V BE2 minus V BE1 divided by VT. Okay. So now it is told IC2 by IC1 is e to the power delta VB, which is nothing but 0.02 volt. So it is 0.02 divided by VT. It is nothing but KT by Q, like thermal voltage. VT is referred to as a thermal voltage. Thermal voltage, where K is the Boltzmann constant, T is the temperature in the absolute temperature in Kelvin, and Q is nothing but the charge of the electron. So if you put this, you will get close to 25 to 26 millivolt, and in the uh, uh, so here also it was told like to take the value of VT as 26 millivolt. So this is 0.026 volt, right? So IC2 by IC1 is e to the so the value I am calculating, just wait. uh, so this value is e to the power minus 20 by 26. Here it will be minus because it got reduction. We have done the reduction, so VB2 is less than VB1, so that's why. So it will be like IC2 is IC1 e to the power minus 20 by 26, and the percentage reduction is nothing but whatever the reduction, that means IC2 minus IC1 divided by IC1 into 100%, right? So if we put the IC1, the value of IC2 minus IC1 divided by IC1 into 100%, so that means, sorry, I have written it in another way, percentage reduction, that means IC1 should be greater, right? IC1 minus IC2 divided by IC1, or it should go in this side, IC1 minus this, that means 1 minus e to the power minus 20 by 26 divided by 1 into 100%. Okay, so this is 1 minus, what is the value, let's see, 20 divided by 26 3 to the power, okay, yeah, 0.463 into 100%, so it will be 53.7%, right? 0.537, yeah, okay, so it is close to 54% or 53.7%. So this is the percentage reduction in the collector current, okay, 54%. So yeah, okay, so see one thing, we are just what is happening if we, so I am just giving some physical interpretation, like if suppose there is this PNP, there is some NPN transistor, let's say here it is emitter, it is base, it is collector, okay, so we are applying some voltage, that is VBE, something the voltage. So if we reduce this voltage, the amount of current that will get reduced, IB, and this IB indeed reduce the value of the collector current, because this IC can be written as beta time IB. So even a small value, small change in IB will reflect a large amount of change in value in the value of IC, because it is multiplied with the beta, and beta usually for the BJT, the beta is very large, very large. So it is close to 99 or 100, like that value. So even if it is very small change, suppose 0.1, so it will be multiplied with 100 times and it will get 10, so it will reflect much more in the value of the collector current. Okay, so that is the physical interpretation of this question. Okay, do you have any doubt, something?
So can you go to previous problem? Can you go to previous problem? Previous
Yeah, this one, yeah,
problem. IB,
yeah,
previous one.
this one,
Okay.
yeah,
No, previous, this one. Yeah. Okay, sir.
this one.
What is the relation between IB and VB, sir?
IV and
VB.
IV,
IB.
IB and VB.
VB. Yeah.
Oh, so what is happening, see, if we apply any some input voltage, suppose the bias is VBB, right, and there is some IV current flowing, and there is some voltage drop, okay, VBE, and there is some suppose this is the resistance RE. So here you are getting one input loop, right? So this VBB, if we apply the KBL, minus IB into there is some resistance, suppose RB, minus this VBE, minus this is the current of IE, right? The emitter current. IERE is equal to 0. So from there also you can find out what is the relation between each of these, whatever you want. You understood, right?
Okay, sir. Okay, sir.
Yeah. Okay. Yeah. So in the circuit shown, assume that the BJT with beta is 120. Okay. So beta is 120 is operating in the active region. What is the value of RB will result in a collector current of 0.8 milliampere. Okay. So here the input voltage is 2 volt. So whatever I have told already, this is the base, this is the emitter, and this is the collector. Okay. So some current that will flow in this side. So it is basically NPN. N, this is P, the base terminal, and the emitter is again the N. So some current that is flowing through this terminal IB, because there is some voltage we are applying. So some current will flow in this direction IB, and in here it will flow some current IE, and the collector current should be IC, right? So we know IE equal to IB plus IC. Okay, so now what is happening, that it is operating activity. What is the value of RB will result in a collector current of this. So this we have to find out the value of the RB. Okay, so if we, so this is this thing is referred to as the input KVL. Okay, this thing is the input KVL, because input means that is base and emitter. Okay, between base and emitter. So if we put the input KVL, that is VI minus IB into RB minus VBE. So there will be certain voltage drop, that is VBE, that is 0.7 volt, it is already mentioned, minus IE into RE is equal to 0, right? So this is V is 2 minus IB into RB minus VB is 0.7 minus IE is nothing but you can say IB plus IC, right, into RE equal to 0. Okay, so if so now what is the value of IB? You know the value of beta, and you know the IC should be beta into IB. Now the value of IC is already told, that the collector current will result 0.8 milliampere is nothing but beta means 120 into IB. So IB is nothing but 0.8 divided by 120, right? This much milliampere, right? See, always beta IB current is very small. The base current, one thing I am telling, that the base current of the transistor is very small. So uh, uh, so you can also learn this from the device parts of point, that because in the base terminal there should be the minority carrier flowing. So this contribute, the current contribution to this is very small. Basically it comes around the microampere range. Okay, and generally the collector current, it comes in the milliampere range. Okay. Okay, so this IB is 0.8 divided by 120 milliampere. So here you can write like and this IC is beta IB, you can write beta IB. So IB, if you take common, it is RB plus, this is 1 plus beta into RE is equal to 1.3, that means 2 minus 0.7. Okay, now RB is nothing but 1.3 divided by IB is 0.8 by 120, right? So 0.8 into 120 minus 1 plus beta is 120, and RE is already given, this is 680, right? So it is 0.68. So we usually write the current in milliampere and the resistance in kilo ohm, so that the unit matches, right? Okay, so if you do this thing, so what, so 1.3 into 120 by 0.8. Yeah, so it is 195 minus this is 121 into 0.68, so it will 82.28 this much kilo ohm. Okay, so it will come minus this. Okay, 102.72 kilo. So here it is, yeah, 113 kilo, close to 113 kilo. You understood, right, this question? Do you have any question regarding this? Do you have any doubt? Okay. Okay, in the next question it is asked, with RB set to value obtained in question 7, that is RB is now what is the value of RB? It is 113 kilo ohm. Okay, so RB is 113 kilo ohm. This is 113 K. What is the value of RC? What is the value of RC? So that this VCE should be equal to 6 volt, right? So what we have already measured, we already know that the value of beta is 120 and the value of IC is 0.8 milliampere. Then the value of IB is nothing but IC divided by beta, that means this much milliampere, right? You know that. So okay, so you know the value of IC now, and so for to find out the value of RC, you should look at this terminal. This is known as the output KVL. So output KVL part. So if you write the equation of KVL, 12 minus, so the current flowing through this is IC, this is IE, and this is IB. So this is IC into RC. So RC, so whatever answer that we will get, that answer should be in kilo ohm, right? Because we are using the milliampere here. Okay, minus this, minus VCE, which is 6 volt, minus IE into RE. IE into RE means IE means IC plus IB, right? So beta plus 1 IB, right? Okay, into RE. Into RE means into RE. Okay, 0.68 equal to 0. So you are getting 12 minus 0.8 into RC minus 6 minus 128 into beta means 0.8 divided by 120 into RE means 0.68 equal to 0. Okay, you got it. So RC is nothing but what is the answer? Okay, so 12 minus 6 minus, okay, so this is 121 divided by 120 into 0.8 into 0.68, so this is 0.54 divided by, so RC is nothing but divided by 0.8, so it will comes out to be yeah, this is 6.8 kilo. So this RC value should be 6.8 kilo ohm. This value of RC is required to obtain the value of VC is equal to 6 volt. Okay, you understood how to apply the input KVL and the output KVL to find out a particular portion. Do you have any doubt? Okay, if you don't have any doubt, then I'm moving forward to the next part. What is the smallest value of RV which will cause the BJT enter into the saturation region? Okay, so basically the saturation region, what happens whenever the BJT enters in the saturation region, the collector emitter voltage is equal to 0.2 volt. So it cannot be lower than that. This VC value should be fixed, that is 0.2 volt. Okay. So now how we can find out that what is the value of this RB that is required. So this VC value is nothing but 0.2 volt, and the RC value we already got in question 8. RC value is how much? 6.8 kilo ohm, right? So it is 6.8 kilo ohm. 6.8 kilo ohm. Okay. Yeah. So this is VCC minus ICRC minus VCE. So this is VCC, this is IC, so ICRC, this is VCE minus IE into RE is equal to 0. Okay. So this VCC is nothing but, so if we take the IC common, so what we are getting, this ICRC plus IE means IC plus IB, right, into RD, okay, is equal to VCC minus VCE. Okay. So this is IC, this is RC plus IC we take common, and IC if we take, then it is the IB, right? So it will come like, so IC is beta IB, so IB is IC by beta. So if IC takes out, it comes as 1 by beta. Okay. RD equal to VCC minus VCE. So this IC is nothing but RC is 6.8 plus beta divided by beta plus 1, right, into RD. RD means 0.68. Okay. And VCC minus VC, VCC is 12 minus 0.2, right? So what is the smallest value of RB? So yeah, so now it will IC, calculate the IC value, that is 12 minus this, that is 11.8 divided by 6.8 plus 120 divided by 121 into 0.68, 11.8 divided by 6.8 plus, okay, so how much it is coming? This is, okay, yeah, so this is 0.674. So that will come like 11.8 divided by 7.474. So it will result in the answer of 1.579 milliampere. And similarly, the IB is nothing but IC by beta equal to 1.579 divided by 120 milliampere. Okay. So you got this from the output KVL, you understood, right? Okay. So you got this thing using this KVL, that is the output KVL. Now from the output KVL you determine the value of the IC. Now if you look to the input KVL, you can easily get IB, because IB is nothing but IC by beta. So from the output KVL you determined IC, and by this equation you got the input value of IB, and now you apply the input KVL to find out the smallest value of the RB, right? Okay. So what happens is, if we apply this, so now for the input side, 2 minus IBRB minus VBE minus IE into RE is equal to 0, or 2 minus IBRB minus VB is 0.7 and I is nothing but beta plus 1 IB, right? IB into RE. RE means 0.68 is equal to 0. Or if you take IB common, then you will get RB plus beta plus 1, that means 121 into 0.68, that is equal to 0, right? So IB is nothing but IB, uh, you know the IB, right? And okay, sorry, you will get 2 minus 0.7 over here. So RB is nothing but 1.3, this 2 minus 0.7 divided by IB. IB you got this thing, so 1.579 into 120 over there, okay, minus 121 into 0.68. This thing goes to this side, okay. So what is the value? I'm calculating, 1 second. 1.3 into 120 divided by 1.579, okay, this is 98.79 kilo ohm, minus this is 121 into 0.68, this is 82.28 kilo ohm, so it will come as 16.5 kilo, okay. So 16.7 kilo ohm will be the right answer. You understood, right, how we usually do the input KVL and the output KVL to find out the particular value of IC or IB? Okay, so we are moving forward to the next question. The circuit shown in the figure behaves like a current source. Current source means there should be some constant current through the load resistors RL. So IL is something fixed irrespective of the RL value. What is the value of RL? Irrespective of that, IL should have some fixed value. As long as RL should be less than RL max, that means if it exceeds to the maximum value, then it cannot act as a current current source. So if the diode voltage drop is taken 0.7 volts, so this is P, this is N, this is P, this is N, this is P, this is N. So here it will be 0.7 volt, 0.7 volt, 0.7 volt, okay. So what is the value of RE required to obtain IL is equal to 1 milliampere? So this is 15 volt. So if we so 0.7 volt drop, so at this point the potential will be 15 volt minus 0.7 volt into 3 diodes are there. So 15 minus 2.1, which is nothing but 12.9 volt, okay. So 12.9 volt is nothing but the voltage in the base. VB is nothing but 12.9 volt, okay. So now what value of RE is required to obtain IL equal to 1 milliampere? So here IL is 1 milliampere, and in the question there is no beta is mentioned, no beta is mentioned. That means the beta is very large, and as I have already discussed in the earlier section, if beta is very large, that refers to the base current is equal to 0, which also refers to the collector current should be the emitter current. So this emitter current is nothing but the load current, right? Because in the emitter we are applied one load RL, and this is emitter current or the load current, we can say. So this IC should be equal to the IL, okay. So now what happens is, so if we apply now the output KVL, that means the KVL in this part, then we get 15 minus IC into RE, right? IC into RE, let me complete that, okay. And there is some voltage drop over here, okay, minus VCE minus ILRL is equal to 0. This is the output KVL. And for the input KVL is like there is some voltage which is VB, that is 12 point, sorry, yeah, 12.9 volt minus so okay, I am doing some mistake, I think. Okay, sorry. Oh, sorry, I am doing one mistake. Silly mistake. Yeah, so this is basically instead of NPN transistor, this is PNP transistor. So you should avoid, you should always look in the question whether it is mentioned like NPN transistor or PNP transistor at first. Okay. So this is the PNP transistor. So this terminal is nothing but the emitter terminal. This terminal is nothing but the base terminal, and this part is nothing but the collector terminal. Yeah, and you should always tell in this way also that in the collector terminal always we put the load. So RL should always be collected in the collector terminal because the collector terminal is the output terminal, right? Okay, so I have done a silly mistake. Okay, whatever. Okay, so I am doing it again. So this is the 15 volt that is applied over here, and there is 0.7 volt drop for each of the diode. So at this input point, that is the VB, sorry, yeah, so in the VB that comes out 15 minus 0.7 into 3, which refers to 12.9 volt. Okay, so 12.9 volt is applied to the VB, and now so there should be some voltage drop, that is this side is P, right? So this is 0.7 because this side is positive and this side is negative. So this VE terminal, this is VE terminal. So VE terminal is nothing but VB plus 0.7, right? You understood, right? So this is 12.9 plus 0.7, which is nothing but 13.6 milliampere, 13.6 milliampere. So this V is 13.6 milliampere, and this is 15 volt, sorry, the 13.6 volt, 13.6 volt, yeah. So 15 volt is over there, 13.6 is volt over here, and we also know the value of the IE, which is nothing but the value in the collector IC, or the load, that is same, that is 1 milliampere. Why? Because beta is equal to infinity or very large, as I have already discussed here, right? IC is equal to IL or equal to I, right? Okay, yeah. So this RE is nothing but 15 minus 15 means this voltage applied minus this VE terminal, what is the value? That is 13.6 milliamp divided by RE. RE means what? Sorry, divided by I means 1 milliampere, 1 milliampere. So it comes out to be 1.4 volt divided by 1 milliampere, which is 1.4 kilo. So the correct answer will be answer B. It is 1.4. So you should always look at first that what is the transistor that is given, either it is PNP or it is NPN, and according to that you should always mention what is the emitter, what is the where is the emitter, where is the base, and where is the collector. You should always point it out, and then only you can move to the to solve the question. Okay, so do you have any doubt regarding this? Okay.
No, sir.
Okay, if you don't have any doubt, okay, we are moving to the next question. Yeah, so this is very interesting question. In this circuit, the same circuit, what is the RL max? That means what is the limit of the value of RL? So if we that means that if we increase the RL more, then it will not be act as a current source or a current meter circuit. Okay, so as I told, always you should look whether it is PNP transistor or NPN transistor. So wherever this sign is given, this should be emitter, right? So and this is base terminal and this is collector terminal, and as the current going from emitter to base, so the current generally goes from P to N. So this is P, this is N, and this is P. So this is PNP transistor. Yeah, you first point out this one and then you should move to solve the question. Okay, so now what is happening? So what is RMS? So we know the current flowing through this is 1 milliampere, and you also know the value of the resistance now, that is 1.4 kilo ohm, that we already achieved in the last question, 1.4 kilo ohm, right? Okay, so it is 1.4 kilo ohm. The current flowing is 1 milliampere. So now and so what is happening, so if it acts as a current source, then it should always be act in the active region, otherwise it will not act as a current source. So if we go to the saturation region, then it will not be the not it will not act as a current source. So uh, for to remain in the active region, the minimum value of the VEC should be 0.2 volt, right? So here it is 0.2 volt. Okay, so if you apply the output KVL, this KVL, then what you are getting, 15 volt minus this 1.4 into 1 milliampere, right, minus zero point 0.2, this is 0.2, right, minus IL is nothing but 1 milliampere, same, into RL is equal to 0, right? So RL is 15 minus 1.4 minus 0.2, that means 15 minus 1.6. Okay, so that will 4 13, so this is 13.4 kilo ohm. Yeah, so this should be 13.4 kilo ohm. This is the maximum value. If we increase more, what happened, the voltage drop here, that will be very large, right? So now what is the voltage around it, 13.4 kilo ohm, right? So yeah, so now it is 13.4 kilo ohm, you got it? Okay, so now you got it, right? It is 13.4 kilo ohm. So 30 and it is 1 milliampere, so 13.4 volt drop is there, and here it is 15 and it is 1.4, so here it is 1.4 volt drop is there. So 13.4 volt plus 1.4 volt, that is 14.8 volt. So rest 0.2 volt appears over here. So if we increase this value more, RL value more, then it will be greater than 13.4, and that will reduce the value from 0.2 to less than 0.2, so which is not possible. So it will go to the saturation region and it will go stick to the 0.2 volt value. Okay, okay, so yeah, so the next question, what is the diode current in the circuit of this? So oh yeah, so this is a very easy question again. So 15 volt is applied over here, and if the diode conducts, then there will be 0.7 volt potential drop across each of the diode. So after 3 diode in series, the potential at this base terminal, it comes out to be 15 minus 0.7 into 3, right? So 15 minus 2.1, right? So it is 12.9 volt, right? Okay, and we know already that beta is very large, that indicates the base current is equal to 0. So whatever current is flowing through this, the base current, there should not be any IB or base current flowing. So rest means whatever current that is flowing through the diode, that should always be flow through this terminal, because the base current is equal to 0, right? So what is the current flowing through this terminal? This is 12.9 volt in this terminal, the voltage, and it is 4.7 k. So the total current flowing through this 4.7 k resistor is 12.9 divided by 4.7, 12.9 12.9 divided by 4.7, so it is 2.74 milliampere, and so this is 12.74 milliampere, sorry, 2.74 milliampere, and this IB is equal to 0. So this entire 2.474 milliampere should flow through the diode. So answer D is the correct answer. What is the diode current flowing through this? Okay, you understood it, right? Do you have any question?
Sir. No, sir.
Okay,
So actually, this data was not given in the question actually.
which one? Oh,
That which one?
beta is very large, right?
0.2.
Oh,
during
no. Actually, yeah,
uh,
here only it is
yeah,
given, right?
yeah, no, like VC should be 0.2. We should consider that thing was not given in question.
Oh, yeah.
So like,
So, uh,
so I got it wrong. Like I was unable to solve that
okay.
parallel max one question. In
Oh,
like there is similar question. They just replace the three diodes by a thinner diode.
oh, is it? Okay, fine. Yeah, so basically what happens is, okay, I am just, okay, so I am going to discuss some fundamental things. Yeah. So this is
Sir,
RB.
like, can you explain once, like, how do we classify whether a transistor is in active mode or a transistor is in like saturation? What
Yeah.
exactly is happening? Like, I try to look at it from the perspective that it has. I just try to look from biasing points of view, but it doesn't give me some convincing answers.
Okay.
Like, I'm able to solve the problems with that.
Okay. Yeah, I am discussing that one only. Okay. Okay. Yeah. So suppose this is NPN transistor. Okay. So this is some emitter terminal, this is the base terminal, and this is the collector terminal. Okay. So now what is happening? So we applied some bias VVB. Okay. So to solve some question, you have to assume, like, as I have already discussed, or you have already seen in the earlier cases, whether to solve a diode problem, you should always first assume that whether the diode is off or on. You should always assume that diode is, means you can assume that the diode is off, and then you find the potential at the of you should find the potential at anode and cathode terminal of the diode. Okay, at anode and cathode terminal of the diode. Okay, so you should always consider the potential at the anode and cathode terminal of the diode and verify whether the anode terminal is less than the cathode terminal. If it verifies the anode terminal voltage is less than the cathode terminal, then your assumption is correct and the diode is off. Okay, and if we find if you found out, like, the anode terminal is not less than the cathode terminal, that means your assumption is wrong. So then you again put diode is equal to on and you try to solve the question, right? So here is similar case. So you first consider that the BJT works as a in a active region. So if it works in an active region, then it should work as an amplifier, and then only IC equal to beta IB, this equation satisfies. So what you do? So you always you try to you apply this input KVL.
So, is this relation valid in all the modes?
Sorry.
IC equal to beta times IB. This relation is valid in all modes.
Yeah, it varies in all mode. Yeah, I'm saying one thing. Suppose if you apply the input KVL, and you find out the value of the beta, and considering it is an active region, this IC is beta times IB, right? And you know the value of the beta. Okay, it is given in the question, or some by something you can know the value of beta. And now you have done this according assuming that the BJT is in the active region, and whenever you find out the IC, then you try to find out what is the value of the VC. If the value of the VC comes out greater than zero point 0.2 volt, we generally consider the 0.2 volt as the saturation and the limit between the saturation and the active region. If you find out the value of the VC is greater than zero point 0.2 volt, then you satisfied that, right, that I have assumed the transistor should be act as an active region, and it is working in the active region as VC is greater than zero point 0.2 volt. And if it comes that the VC value is less than zero point 0.2 volt, suppose 0.1 volt, then you should know that, no, my assumption that the this works as an active region, that is wrong. So you should strict the value of VC equal to zero point 0.2 volt, and using the back calculation you should find out the value of the IC and then the value of the IB. So in by this case means by this method you can find out whether the transistor acts is active region or not, or is in saturation region, like that.
Okay, sir.
Okay. Yeah.
And what about, sir, cutoff?
Okay, so basically the cutoff region when both are in the reverse bias, you apply the VB in this VB is in the negative, that means in the reverse bias condition. So that means that there should not be any that means this base emitter terminal is the reverse bias. So that means this transistor works as a cutoff region. Okay.
So, like, what is the characteristics that we can say that it is, if it is this, then it is in cutoff region?
Cutoff region, that
Like you
means,
said, no,
yeah,
like for saturation, you said that VC is greater than 0.2,
yeah,
it's in active region, and if it goes smaller than, if our assumption makes it smaller than 0.2,
yeah.
then we should consider it at 0.2 and consider it as in saturation region, right?
Yeah. So the thing is, like, suppose there is no register, okay, so this terminal is grounded, so this VB is 0.7 volt. So you should always make the voltage should appear more than 0.7 volt over here, then only this PN junction will operate, right? Then only the current will conduct. But if it is the voltage is like the no current is flowing through that, then there should not be any current conduction in this region. So that means the transistor is basically in the off it is in cutoff region, or no current is conducting, right? You got it, right?
Okay, okay, yes, sir. So in saturation region, IE is 0, right?
uh, in sa-
IE, IB, IC, all are 0.
in saturation region, no, that is not really the
In
case.
cutoff.
In cutoff, yeah. So this IB is, yeah, so this basically this IB is, yeah, 0. That means the IC is also is equal to 0. Yeah.
Okay, okay, sir.
Okay. Okay. So in this circuit,
So, like, what we should do when two terminals are like just shorted.
two
Like,
terminal
suppose the base and collector terminals are shorted.
base and collector terminals are shorted.
Uh, like, what to do in this such cases?
So
Like, there is no bias right here. Like, the difference in B and the base collector voltage difference is 0.
voltage, sorry.
The base collector voltage difference is 0, right?
Yeah.
So in such cases, what we should do?
Mm,
Like, what
and
comment we can make on the current going?
okay. So if there is some register, there should be a current flow. This is IC, and this current. Uh, so basically, I think that there should not be flow of current, because if you just shorted the base collector, so in a this is emitter, this is base, and this is collector. So you are not putting any bias in that, so the current will not flow, right? So the IC will be is equal to 0, because this PN junction is like that will not conduct basically. So how can the current go to the collector terminal?
Sir, like with this, like I was unable to get this similar question was asked in week 5 assignment.
Okay.
There was something like mirror circuit. I searched on internet and I got it. Something mirror. They do something. Two transistors were there actually.
Sorry.
There were two transistors.
Okay, okay. Oh yeah. So like this, right? So
Yes, sir. Yes, sir.
oh, so
Exactly.
okay, okay. So these should be connected like this. Okay.
No, not both, sir. Not
Always
both
single.
were
Yeah,
shorted.
yeah.
Only one.
Okay.
Like they gave hint. The hint was given that you should do assume both in active mode, but how can we assume it in active mode? I didn't get it.
Oh, is it okay? Hmm. Okay, I'm not very sure. I have to look into it. Okay, I will get it to you in the next session. Okay.
Okay, sir.
Okay.
Like this is like in my general doubt only. Like I am unable to solve when there are two transistors together.
Okay.
How should we make assumptions and all that I didn't get.
Okay, I got it. Okay, okay. I will discuss it to you.
Next session, right, sir?
Okay. So for this question in this circuit, the BJT has a large beta. That means beta is very large. That is infinity, and alpha is tends to 0. Sorry, alpha is tends to 1. So I is basically is equal to IC. What value of VV is required to obtain IC is 1.2 milliampere. So you should apply this. This is the NPN. So whatever IC is there, that much IE over there. So if it is 1.2 milliampere, it should always be 1.2 milliampere. So this is the emitter terminal, this is the base terminal, this is the collector terminal. So the emitter terminal VE is nothing but IE into RE, that means 1.2 milliampere into 0.68, this thing, and here it is minus 5. So minus 5, so it is 1.2 0.68. Okay, so it is minus 4.184. Okay, now you have a voltage drop VVE. So this VVE is 0.7, that means VV minus VE 0.7. VV is nothing but 0.7 plus VE. So 0.7 minus 4.184, it is equal to 3.
Yes, sir. Approximately minus 3.
Yeah, approximately it will be like 3.5 volt, right? Okay, yeah. So now in the circuit, what value of VV is required to make IC is 5 milliampere. Okay, so now IB is equal to 0, so IC and IE both are same, which is 5. Similarly VE, as we have already discussed, minus 5 plus 5 milliampere is flowing through 6.8, so minus 5 plus 5 into, so half of this, that means 0.34. Yeah, so it is minus 1.6. Hello. Okay, so this is basically minus 0.16 volt. This is the value of the VE, and VBE is 0.7 volt. That means VB is nothing but 0.7 plus VE. So it is 0.7 plus 1.6. Okay, so sorry, 0.7 minus 1.6, that is refers to minus 0.9 volt. So the correct answer will be answer A, that is minus 0.9 volt. Okay, so I am I audible? Am I audible? Hello, hello.
Audible.
Yeah, sure. Okay, yeah. So it's the last question. Okay, so what is the maximum value of VB for which the BJT operates in the active mode? Okay, so again the same thing, that is the beta is very large, that indicates that IB is equal to 0, that indicates is I equal to IC. So if we apply 5 minus 0.82, that is the output for the output KVL, 0.82
So
into,
your screen is not visible.
oh sorry, I forgot to share my screen after joining this. Now is it visible? Now is
No,
it
sir.
visible? Now is it visible?
No, sir.
Oh, is it? I have already shared. Just check once. Now is it visible?
No, sir.
Oh, is it okay? Yeah, I am stop the sharing and again going to share. Now, actually, I am able to see that I am in presenting mode.
Okay, I need to off and I need to get the list.
Yeah, please rejoin.
Yes, sir. Now it is visible. Yes.
Yeah, no? Okay. Yeah, fine.
Yeah.
Yeah, thanks.
Yes, sir. Now it is. Yeah.
Okay, so yeah, so beta is very large. So IB is equal to 0, which means I equal to IC. So this IE and IC, sorry, this is IC and this is IE, both are the same. So 5 minus 0.82 into that 0.82 we have already derived, right? So 0.82 into, sorry, 0.82 is the resistance into the current, which is IC minus, so this is active mode, should operate in active mode, should, so this should be at least greater than 0.2 volt. So minus 0.2 volt minus 0.68, which is this thing, into IE is basically same as IC. So we can refer to the IC also, minus, this is minus 5 volt, so minus of minus 5 is equal to 0. So IC is basically 0.82 plus 0.68 rest of the things goes to this side, that is 9.8. so IC is basically 9.8 divided by 8 into 10, so it's 1.5, which is 9.8 divided by 1.5. okay, so 6.53 milliampere. So 6.53 milliampere is IC. So what is the voltage across VE? V is nothing but, here it is already minus 5 volt plus this drop, that is minus plus 0.68 into 4.53. So this is, just one second, 9.8 divided by 1 point, oh sorry, it is 6.53, made a mistake. This is 6.53, okay, 6.53. so minus 5 plus 6.53 into 0.68, so it is 4.44. so it will be like minus 5, so minus 0.5596, so like that. And they are asking about the VB, so we know that VB is 0.7 volt, that means VB minus VE is 0.7 volt, that means VB is nothing but 0.7 plus 0.5596. okay, so this is 0.7 plus 0.5596, it is minus, sorry, 0.7 minus 0.5596, which is minus, sorry, plus 0.1404, this much volt. So it will be answer D. Okay, so do you have any question regarding this?
No, sir.
Okay, actually I want to discuss one thing. So you are not aware of the MOSFET. So basically in the MOSFET, what it does, like suppose this is a MOSFET, so this is similar similar to the BJT. So instead of base we call it as gate, this is the source instead of emitter, and instead of collector we call it as drain. So what happens is basically the MOS is in active region, that means it is on the active region when VDS is greater than VGS minus VTH. okay, so whenever it is in the triode region. okay, so what happens is, uh, someone was asked like, if what will happen if we short the drain and the gate terminal, the transistor will be off or on. So what happened in case of this, like VT minus VS, you can write this VG minus VS minus VTH. okay, so this TH is nothing but the threshold voltage. okay, so this source and source cancel out, so VD should be VG minus VTH, and this is basically a NMOS. okay, so for NMOS VT is always a positive number. So what happens if drain and gate is always shorted, then we can write VD is equal to VG. So VG should be greater than VG minus VT for the to turn the MOS in active region. So now see in this equation, as VTH is always a positive number, this equation always satisfied irrespective of what voltage we applied in VG or VD terminal. So that means this MOS is always be on. So similar will be the case of the BJT if we consider the similar thing in the BJT also. So there is a base, there is a emitter, and there is a collector. So this BJT will act as in active region if this VCE should be greater than VBE minus VTH. That means if we are applying some voltage in the base terminal, and if it is greater than this VTH, that means this threshold voltage, if it is greater than, then some this VC, if it is greater than this thing, then that will that thing then this will be turned on. That means that will act as active region. And if VB is connected to the VC, then this VC is equal to VB minus VTH. We are eliminating V, and VC and VB both are same, so this condition always satisfied, so this is always on. So probably for that reason it will always conduct, it will not be turned off, but rather we can always, it will always conduct. Okay, yeah, fine. Okay, so do you have any doubt or something, more doubt or something?
That means it will be in active region always.
Yeah, it will be in active region always. So whenever you will learn about the MOS topology or conventional MOS, then this concept will be more clear to you. So actually the BJT and MOS both operate in a similar kind. There are some minor differences, like in the MOS there is some only one kind of carriers are there, that is the majority carrier. If it is NMOS, the electron majority is the majority carrier, that means the current contacts is dominated by electron, we don't consider the hole. But here it is bipolar, that means there are hole and electron both, majority minority both. In case of NPN, electron is majority, in case of PNP, hole is majority. So that is why this BJT is known as bipolar and MOS is unipolar. So like that. So I think Professor Patil will discuss more about that when he will talk about this MOS. Okay.
Okay, sir.
Okay. Do you have any doubt regarding any of the question or something? Yeah.
Yes, can you explain the average cancellations are in the first question you explained?
Oh, actually you have to plot the capacitor one, the curve of the capacitor and also the diode. So it will be better if we discuss in the next class, because it will take much more time. Or you can
No, approximately how it is. It not exact, approximate, just a general hint.
this one, right? So what happened is
Yes.
yeah, so what happened is there is some capacity, there is some current flowing whenever the diode is turns on, then the current will flow through the uh, then the current will flow to the
Capacity.
capacitor, yeah, and the capacitor will get charged. So the current will be like I equal to C dV dt.
Hmm.
So it will be like C d dt of Vm sine omega t. So it will be like C Vm omega of cos omega t. So that is the thing. So if you plot that curve, that means this thing, whenever the capacitor is this thing, and whenever it is getting discharged, that means it will get discharged, eventually get discharged in this point. So if you calculate this thing, you can find out that this area will be all equal to this area. So that means the average is basically the zero. So these two both are not same, the time domain for this time is more, but the overall area in this region will be exactly equal to the area in this region. That means that will be cancelled out, and for that reason only this IC average value becomes to zero.
Okay, sir.
So what
Okay.
concept is like this? Yeah, you understood, right? Yeah,
Yes, sir. Yes, sir. I understand.
yeah. Okay, so I will recommend it to you to see the lecture more or more deeply, or try to analyze the question. Yeah, sometimes some question becomes tricky, I understand, but you have to think more actually. Instantly, it doesn't come to mind at an instant, but if you think more, you can easily solve. Okay, or
So
if you
more the conduction means lesser the ripple or more ripple.
sorry,
More the conduction of the diode.
more the conduction of the actually ripple does not the ripple means that is that how much the uh, AC, how much AC is content in your from your rectifier. That means how much the ideally it should be a constant value, the DC. So how much AC is there, that depends on the ripple. It is not about the more the conduction or less the conduction. So
Okay, sir.
it can be determined by this filter also, the RNC value, what is the RNC value, like that. Understood, right?
Yes, sir.
Okay.
Yes, sir.
Okay, so today I will end this session. I have some other work also. So we will meet in the next Tuesday, 6 to 8. Hello? Hello? Okay, right?